Yeah, so it's a lot better than what I can draw. And I think this is really for the next class period, this rotational, vibrational spectroscopy. And if you remember this vibrational spectroscopy, it's like a step ladder, right? But each step in the ladder is a different vibrational energy level. And you just jump up that ladder, just the amplitude changes. Remember, the frequency doesn't change. It's like pulling down the spring further, right, in that bouncing, hanging weight. And except with the bouncing, hanging weight, you can only pull it down certain distances because energy is quantized, right? Well, each distance that you can pull it down, here you see it, watching it vibrate up and down, but it has its own set of rotational energy levels. And that's what this is. So this is just one vibrational energy level, but you look at all these guys, and they're rotational energy levels. And the more intense they are, the more populated they are. But I just wanted to show you that because we're going to pretty much be talking about that, I think, the next class period. But those are the angel wings I was trying to draw before. So we are still talking about rotational motion and rotational energy levels since energy is quantized, right? It sounds odd that, I mean, if you have a little molecule rotating, why can't it rotate any speed it wants? But that's just not how life is. So if we want to explain it well, that's just not how it works. So we have a term, a rotational constant term. B is h bar over 4 pi ci. Now there's some conventions here. This has units of centimeters to the -1. And we're not supposed to say centimeters to the -1. We're supposed to call that unit a wave number. We're supposed to call that unit a wave number. And one thing I think you just got to get used to, and we don't like talking this way. If I tell you so many joules, we know it's energy, right? That, oh, this is the energy of this state, and you give it the answer in joules. But I don't have to give the answer in joules. I could say nanometers, and then you have to do a little bit of math, and you calculate the joules. I could tell you frequency, do a little bit of math, calculate the joules. I could give you wave numbers, and then do a little bit of math, calculate the joules. So just try to get used to them saying wave numbers. Oh, they're talking about a state, and that's a particular energy, right? So that's kind of where this is coming from. So if that's in wave numbers, I think to make this thing work, c is in speed of light, but have it in centimeters per second. And we'll do some homework, but I'm pretty sure that's all you need to do to make sure that your b is in wave numbers. Just make the speed of light in centimeters per second. Everything seems to work out. What's h bar? H over 2 pi. Good, so we got that one. How about this I? Mm-mm.
Intensity?
Mm-mm. It's this rotating object, so it's motion of the entire molecule, so you have to take, I don't know if that's a hint, reduce mass into account. It's the moment of inertia. And where do you get that stuff? Pretty much from this table. But pretty much the only thing we're ever going to worry about is this. So your moment of inertia is always that. Okay, so that's pretty much all we're going to be messing with. These rigid rotors, right? Why'd they call them rigid rotors, Melissa? All these different shapes of molecules. I don't know if you remember your valence, shell, electron, pair, repulsion theory, but you can come up with all these fancy shapes, right? Jeffrey, you remember how to name this one? It's got a square in the middle. Close. Square pyramidal if if I could erase that one. Square planar if I could erase both top and bottom.
Is it square bipyramidal?
Square bipyramidal would be this one. Yeah. Okay, so that's it's neither here nor there. Just seeing if you remember that stuff. Okay. But you could predict the shape of that molecule using the Sepper theory, and then okay, it rotates. Well, if it's a rigid rotor, it doesn't do what under rotation?
Stretch.
Yeah, stretch. But they use the D word, and it's not damn it. distort. All right, that's what they're trying to say. They won't distort. Okay. So we've got some rotational quantum numbers here. We've got big J. K, I haven't seen K. M sub J. Okay. So these rotational terms, here's our energy. But again, when I say wave numbers, energy, same thing, because you can calculate it, right? So there's our energy of our different states. So you recognize there's our rotational constant, our B. And then it just depends on the rotational quantum number, J. I don't know if you remember this, but M, for every J, there's how many M sub J's? How do you figure out M sub J again? Or M sub anything, really. It goes from the negative to the positive. So everything is, what would that be? If 3, that would be 6 plus 1, 7. So it would be J, 2mj plus 1. I'm trying to figure all the different states, right? If J was 1, M sub J would be negative 1, 0, 1. All I'm driving at is that M sub J, we don't even care. Look, it's not even here. So that means what they're saying without saying it is that for, okay, what rotational state are you in? Just describe J. But realize that it's degenerate, right? There's actually, all right, 2mj plus 1 states there, right? 2j plus 1 states. There's actually 2j plus 1 states for every j. So even though we draw just one line, there's a lot of degeneracy going on there. Okay, but we'll hit on that again in a little bit. But what's kind of interesting, I think, let's make this a you-do. Oh, let's do this now because Gloriana might feel a little bit better.
Thank you.
Who got the high score on the last exam?
I did.
I didn't want to squeeze your hand.
It's a dream come true. Oh my god. Yay, gee.
She beat somebody by 1 point.
I really didn't think I was going to do that hot.
Okay.
I passed it, I'm happy.
Oh, okay. I was going to do a you-do. So this is how you get the energy of any state, right? Just say a J. Well, what's the energy difference between these states? If you take f of j minus f of j minus 1. So take this, subtract out, then put in j minus 1 in there for everything, right? You'll do, this is a you do, because you need this for the homework. 2bj. That's the energy separation between these j's, these different rotational states. 2 times b times j. So as j gets higher, that's why they plotted this one out. As j gets higher, right? Look at the spacing, gets bigger and bigger. Well, yeah, because 2b times j gets bigger and bigger as j gets higher. So the spacing between these rotational energy levels gets bigger as j gets bigger. Okay. And it gets kind of confusing because they also call it a constant. They say the spacing between rotational energy levels is a constant, 2bj. But that constant's changing all the time. So it's just something to get used to. Okay, but this, right, they call that, oh, that's the constant spacing of the rotational energy levels. Okay, but it's not really a constant, right, because j changes. Make sense? Okay, principal axis. That's that chapter 15 that we skipped, except the inorganic people didn't. They just loved it. And they talked about principal axis a lot. And notice how there's these different moments of inertia. Right? There's I parallel, I perpendicular. And since all of our homework pretty much is just linear rotor, we don't need to worry about that. But that principal axis comes into play when you start talking about more complicated molecules with actually some symmetry to talk about. And do you remember how to define that? Who had inorganic? Mel, you had inorganic, right? What was a principal axis?
Isn't that the axis that has the biggest n value? Like,
Yes.
like
Woohoo! Okay. So here's my principal axis. And for rotating, just if you haven't had inorganic, you don't need to worry about this. It's just FYI, right? They call these rotations, they have a C symbol. So that means I'm going to be rotating. And I want to rotate it and get the exact same looking molecule again. So this, that you rotate right through here, rotate through this atom, and this atom, and you get this rotational axis. And that would be a C what? It's the principal axis, has the highest end. That would be a C. How many corners? That's the easy way. 4, it's just C4. I mean, you can do the math and figure out that it's whatever degrees. 9, I don't know, 90.
Yeah, 268
Right?
to 94. Yeah.
So don't really worry about it. But that's the point. So they were talking about that just because they forced you through chapter 15. And we're not going to worry about oblate and prolate, so don't worry about it. Okay. I think here, can you read what this says?
Field off.
Field off. What field?
Electric field?
Electric field. So if you turn on this electric field, boom, what we said doesn't show up in the term symbol, all of a sudden shows up, those M sub J's. So which was just one level, right? All that degeneracy pops open when you turn on an electric field. But whoever does spectroscopy in a really strong electric field, nobody. So we really don't see this. Like the FTIR and all those things, we're not applying a huge electric field across everything. Okay. But they call it the Stark effect when you turn on that electric field. I wouldn't really worry about it too much. But okay. Well, let's just make sure here J is, make sure you remember. Let's say J is, it says 7, I think, down there. If J is 7, how many different M sub J values are there? 15. So that would be actually 15 lines you'd see. Okay. Centrifugal distortion constant. Now, I don't know. My physics, I loved physics, and my grades just weren't that great in it. Otherwise, I would have majored in physics. There's something wrong with this picture. And if you love physics, I think you know what's wrong.
Is that picture?
This picture. No, there's no cross product or anything here. There's, you guys don't catch it?
So no arrows, the direction of the arrows going out.
Well, what is it trying to illustrate? What's this green arrow trying to show you?
Spinning.
It's spinning. Okay, it's spinning, going around, 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 around. So these little atoms on the end, they want to go where? Out. So there's nothing wrong with the arrows, right? That makes sense, right? The problem is this. This spinning object has one force to describe its, right? There's one force here. Angular momentum is not a force, it's momentum. There's one force here in any object that's spinning. What's the force?
Centrifugal.
Centripetal force. Well, what the heck is this made-up thing? What are they trying to say here? There's no such thing as centrifugal force. You put something in a centrifuge, right? You turn it on, it whips all the heavy stuff to the bottom, pulls it all to the outside. Oh, that's due to centrifugal force. The only force there is centripetal, and it's pulling everything towards the center, which is what keeps it going in the circle in the first place. So why does all this stuff get on the bottom of the test tube? Why do these little atoms feel like they're going to get pulled towards the outside? If it's not a force, what is it? Starts with an I.
Inertia.
Inertia. It's mass. An object going at a same speed, same direction, keeps going in that same speed, same direction until acted upon by an unbalanced force. That's Newton's third law. But the point is it's inertia. It has mass. So that's why it's going outwards, right? It's not. It's just that word right here, force, is what bugs me. Okay. But everyone knows what they mean, so they really don't care. So if you have this centrifugal distortion going on, well, that means it's no longer a, what do we call these guys? We call them rigid rotors. They're no longer rigid rotors if they're distorting. Well, if there aren't rigid rotors, that means this equation's all messed up. That means this is messed up. So they throw in a little fudge factor here, distortion constant. That's what that DJ is. So your spacing between energy levels, if you have centrifugal distortion going on, is that. So in the homework, they're going to say, if I remember this right, that's what I was trying to look before we started. The homework, I believe, says something like, well, in this constant spacing rotational spectrum, if it's constant spacing, they're not talking about this. They're talking about constant spacing, this thing that you had to do 2BJ. Right? If they say there's centrifugal distortion, and then 2BJ is not valid, that's not going to be the separation between rotational energy levels anymore. Then you have to go and mess with this. And here's where our centrifugal distortion constant is. Okay. Okay, I think that's good enough on that. Rotational transitions. So you get this nice, beautiful angel wings, which I deleted. Shoot. Do you remember the angel wings? You get the nice, beautiful angel wings when you have, this is carbon monoxide. Yeah, carbon monoxide. When a molecule has a permanent dipole moment, you get this nice, beautiful things. Now, and I don't remember if the homework is going to get you on this. It might. If Chapter 15 said you had to be a member of what point groups? CN, CNV, and there's a third one. CS. Thank you, CS. If you're a member of those point groups, then you have a permanent dipole moment, and it'll exhibit this. But since we're always talking about rigid rotors, I don't think you really need to worry about this because you just look at this guy. How do you know something is a permanent dipole moment? How do you know what? If it's polar all the time. And how do you know if something's polar all the time? Permanent dipole moment, yeah. To me, visually, it goes back to the Sepper theory, right? You look and see if all the dipole moments are canceled out or not. I mean, who really cares about this whole, CN, CNV, CS? Just look at it, you can tell, right? For example, let's say all the atoms are the same. So these are all MAs, right? Make that an MA. Would that have a permanent dipole moment? No. Yeah, they all cancel out. So all the perfectly symmetric shapes, they're always perfectly cancel out.
Okay. I'm having issues with the dipole, so like, what does it mean like if they all cancel out?
If they all cancel out, that means it's non-polar. Non-polar. So that means...
So they just cancel out because they're opposite of each other?
Well, usually, here, yeah. Then it's real obvious that they're perfectly opposite. But here it's mathematical. This electronegativity tug is canceled out by these pulling out at 33% power, each one of them, right? Their net cancels it out. So they're not perfectly lined up, so it makes it harder to see. But here, this one is easy to see. All right, this one, call them all MAs again, but...
Like the one in the middle of that is polar.
Well, this one we don't even care about.
No, the other, that one.
Oh, this guy, yeah, he'd definitely be polar. Definitely. Permanent dipole moment. This would exhibit a pure rotational vibrational spectrum. You would get a nice angel wings from him. Good. What happened? Oh, we're here. Okay. I should have. Now I got to write all this. Our first selection rule. Right, for these rotational transitions, we want to go from J to J plus 1. Well, you can't really make any transition. I think what this is coming from is delta J has to be plus or minus 1, and M sub J is 0, right? Did I write that down? Oh, it could also be plus or minus 1. 0 or plus or minus 1. So what are the allowed wave numbers? This is just, I just copied this from the book. So this is coming from this. They did the math for us. We don't have to worry about it. Okay, what were they? 2b times j plus 1. Those are our allowed wave numbers. Remember, we had some selection rules once before. I think we came up with a couple before, but we haven't had very much. Rotational Raman spectra. For what had to happen, let's back up a little bit. If you're using the FTIR, what must that molecule be exhibiting to absorb heat? What must that molecule be exhibiting? If it's not doing this, it can't absorb IR radiation. It's kind of a selection rule, but it's the concept of it. Had to have an oscillating dipole moment. That vibration had to have an oscillating, some magnitude. The magnitude of that dipole had to be changing. And it's changing at the same frequency as the incoming radiation, and then it'll absorb it. So that was the idea with FTIR. How about rotational Raman? What about Raman spectroscopy? The molecule had to exhibit what? This is those two words, long, complicated, ugly. And
oh, it was the anisotropic polar well, I can't say it.
yes. Yes, anisotropic polarizability. Yes. Okay, so what did that mean? Now, it's supposed to be more general.
That you can polarize in different regions.
Exactly. You can polarize that molecule differently in different regions of the molecule. And then it'll exhibit Raman spectroscopy. Okay. And Raman, was that, what type of interaction was that? I mean, it's all spectroscopy is interaction between light and matter. FTIR, there's absorption. Raman is supposed to be what? Not so much, ooh, this photon comes in and it gets absorbed. The photon comes in and it gets, kind of, not really emitted. Because emitted to me means it absorbs, goes to its excited state, and does something. This is more like the S word. It gets doing, doing, doing. It gets scattered, right? Right. So it's kind of a fine line. I mean, because remember, the scattered radiation can be exactly the same as the incoming radiation, but then that was an elastic collision, which was not so much Raman as it's called Rayleigh, right? Yeah, that's this, right, this center line here, right? Completely elastic scattering, Rayleigh scattering. But typically the Raman event, the you get the scattered radiation and the outgoing, the scattered radiation is either a little higher or a little bit lower in frequency than the incoming radiation. So they're elastic. Sorry, they're inelastic collisions, right? Okay. Let's see if you're following me here. Carbon tetrachloride versus water. One of them is invisible to Raman spectroscopy. Which one's invisible? Can't even see it. It's like injecting hydrogen onto the gas chromatograph with hydrogen as a mobile phase. You can't even see it.
Maybe water.
Water? Now remember, it has to be, if you can't see it with rotational Raman, it means that, man, it's the same polarizability everywhere. Use that Vsepper theory if you remember it. Right? Do you remember water?
Bent.
Water was bent. So just it being bent, it's polar in the first place. So it's definitely ice. That's polarized differently in different regions. Just off the bat, it's a polar molecule in the first place. Carbon tetrachloride. Oh man, what a mess in here. Which one of these things?
The first one is symmetric rotors. Okay.
This one, right?
Mm-hmm.
Yeah. What shape is that? It starts with the T. Tetrahedral. So you have this photon comes in and electrons interact, right? It polarizes it a little bit in some region. Well, heck, this molecule's perfectly symmetric, so you can't really tell, right? It could have came in on this region, it could have came in this region. It completely isotropic polarizability because that molecule is perfectly symmetric. So that's the only time you can't see Raman molecules, if they're the ones that are perfectly symmetric. Okay, so we're supposed to write down a selection rule here.
So you can't see Raman if it's perfectly symmetric?
Yeah, so this would be invisible. Can you envision carbon tetrachloride being visible on the FTIR?
No.
Can you imagine it being visible? In other words, what you have to imagine a vibration, because we're talking about FTIR, you have to imagine a vibration that's not perfectly symmetric. And then you got it. Right? So you could have some chlorines going out while the other sides are going in. So it's not a perfectly symmetric vibration. It's not a perfectly symmetric stretch. Then you're going to have an oscillating dipole. It'll absorb. Okay, so we're going to write down the linear rotor selection rule. This is the only one they gave us, so this is the only one we're going to worry about. Or maybe this is the only one that the homework cares about. I should have had it written down so I could do this. So delta J is plus or minus 2 now, because we're talking about Raman. So the wave number for the J going to J plus 2 state is, they have a little I. They have a wave number with a little I on it. We'll talk about what that means. Minus 2B J plus, whoop, I forgot my numbers here. 2J plus 3. Okay, now with Raman spectroscopy, it's a what event? Not so much an absorption event, it's a scattering event. So that means you need to have some incident radiation for it to get scattered, and that's what this is. That's the incident light, the light that's incoming to be scattered. Here, there, if we did the math, we're not going to do this. I'm just going to give you the answer. The separation of these energy levels is 4B. And B is what units?
Wave numbers?
Wave numbers. Yep. So I don't know, the book got into this. They're just trying to say, why does Raman have delta J plus or minus 2? And what it gets into is I think just it gets into even states. I don't think you need to worry about this. It gets into even states. It has something to do with the Pauli exclusion principle. I wouldn't worry about it, even though I'm writing it down. Don't worry about this. DWA. Okay. I think we're pretty much in this one. We're not going to worry about it either. So let's go ahead and take a look at some of these. If the wave number for the J 2 to 3 rotational transition of HCl is considered as a rigid rotor, wave number 63.56 wave numbers, what is the moment of inertia of the molecules and the bond length? Okay. What mathematical symbol is moment of inertia? Big I. Big I. So they're after big I. And then bond length. Do you see where that's going to be coming from? Because where do you get these big I's from? That chart. Right? So here we go. The second part of the question wanted to know the bond length. Well, in that expression I circled, what's going to be the bond length? There's one atom, here's an H, here's a Cl. The bond length is R. Right, so there's our R, there's our bond length. So that's what we're after. I think we have everything we need, don't we?
So we used that very first equation and saw us off for I.
Oh, they gave us the wave number, didn't they?
So it's going to be the H bar.
Oh, yeah. There's our I, right? And our wave number. Do you see why this is the wave number? Do you see why that's the wave number?
You said because the energy levels are as J increases,
Yeah.
the energy levels are
Yeah, because if it's going to jump from one energy level to the other, it's going to be the energy separation. So we don't plug in just one of these. We don't want the energy of one state. We want this wave number was absorbed. So they're talking about an, yeah, so they're talking about an energy difference. So when they say, go back here, when they say that it underwent a transition, right? So they're talking about one state to another state. That energy is 63.56 wave numbers. And that's where I think it gets confusing. I mean, when you think of energy, I don't think of wave numbers, I think of joules. So if they would have said, oh, the energy was this many joules, I think we would have, and would have seen joules up here before, it would have sunk in right away. So they have to be the same. So we'll set them equal. And out of that B, so we got some math to do. Out of that B, that's how we'll get our I. Right? Then once you get your I, then you can get your R. Make sense? So this would be done first. Second, right? Get your I, third, then you get your R.
So the original wave number we're given in the question goes into that?
Yeah, that original wave number is this energy separation. Right?
Yeah, that's in there.
Oh, what was it from J? J to C.
What's it called?
I think that's all I did. Oh, one other thing I did. When you're after this R, you set I equals mu R squared. Life is a lot easier using the, I should have wrote it down here, what the problem is. It's a lot easier using, 'cause why do they give you these superscripts? I word, isotopes. So it's a lot easier to keep everything in terms of U's, because all you do is just look them up in the table, right? And I mean, you don't have to. You can go ahead and calculate the kilograms of these, but you don't have those. You have all the answers in terms of U. So I would go calculate that reduced mass in terms of mu. Now, how do you get reduced mass again? It's in the book. There it is. Right? What's the M on the bottom? Total. You just add them up, right? So I would put everything in terms of U. And then to get back into kilograms, remember we have that little conversion factor. I forget what exactly it was. There's, right? Remember that? Remember that? To get back into kilograms.
Oh, that number. I just written down somewhere.
Yeah, it's in the inside front cover of my book, and I don't know where my book is.
1.660577 times 10 to the minus 27. 1 meter.
Yeah. So that's how I did it. It was the easiest. Okay. Really, you don't have much choice because they told you the isotopes. So that's what I kind of thought. This homework was kind of the same thing over and over and over.
So then can we just do 16.3 together, so that way
Yeah.
I'm still a little confused
All right.
as to how to set the equations equally.
So go ahead and see if you can do 16.3. And I'll give you some time to get started, and then I'll show you what I did. All right?
Dr. Smith, can you like scroll back up?
Really quick.
More. Yeah, right there. Oh, a
Okay,
little
I
bit
have
more.
it.
A little bit more.
I have it.
Oh, okay. Never mind, I got it.
Oh, the 1 point.
Yeah.
Yeah,
Oh, this guy. Yeah.
So the J you're ending
Which
up
J are
in?
you going to
The
use?
one you end up in? Or is it the one you started off in?
I think that the only hint you have. So did you hear Melissa's question? What J do you use?
Oh, the bigger number.
You use the bigger one. Otherwise, this doesn't work, right? You have to use the bigger J because you see it's f of j minus 1, so it has to be the bigger J. J has to be the bigger one. Good question.
like, can you scroll down?
You didn't get them they didn't get typed out in yours?
No, I don't have any of the
Man.
problems typed out on any. It's just, it's in the one that you sent us, but
Well, all semester it's been like that, right?
yeah.
Yeah.
Do with B again?
Do that, the one that was TBJ
So it would be
Right.
2 times the 63?
times the bigger J.
Which is 3.
Oh, I see. We're swirling and stuff.
So I skipped a lot. Remember, the trick, I think, is just getting that C in centimeters per second, and then everything else will be okay. Just leave everything else in metric. Well, the only other thing is H bar. But so if you put, just make sure you do that. Make sure C is in centimeters per second. Three times 10 to the, but centimeters per second would be 10, right? Yeah. So make sure that you have that as your C. It should work out. Product over their sum, right? Yeah. Is that 35 CL? Probably take that times That's kind of a skeleton how I did the whole thing. Because in the end, I had to get this mu in terms of kilograms, right? Because look at your moment of inertia has kilograms in it, so you can't leave that u there. So you got to get rid of it in that last step. And where you get these masses, this inside front cover, which I don't know where my book is, and you look up what those are. Does anybody bring their book?
I don't know.
I think, aren't they all here? Or am I just imagining this? Yeah, here they are. Do you remember, so it's the inside front cover. So remember what the slash u means? Like here they have this column with all m's. It's the units. So that's exactly what you want. You want 1.0078 u. That's what H1 is. And then chlorine 35, 34.9688 u. That's what you use for them.
What was
Hydrogen
hydrogen?
is 1.0078. And chlorine 35 is 34.9688. So simplify that and then convert it into kilograms.
Okay, so I got the part, like I understood why we had to set it up like this, but then when you did the 2 times that entire equation.
So exact 2 times this whole thing,
'Cause that's
and then
B, right?
times my
Convert
j,
it to
which is
kilograms.
3.
Yeah, using that
Oh,
equation.
okay.
Because j has to be the higher one.
So you can't just use the 63 as B?
The MH and the MCl, you'll replace it with the...
This is the wave number. That is equal to 2bj, which is equal to this. But this doesn't do us any good.
Okay.
So you said really this is equal to that, or those two. And we're going to solve for I.
So then once we get whatever this is,
Once you solve, you have to solve for I. So substitute in what b is.
which is a 63, right?
B is this.
Oh.
No, this is your wave number.
That's
Equal to this whole thing. So it's kind of
okay.
like this. You're going from one state to another state. So for it to jump up there, it has to absorb this energy. So this difference in energy is 2bj. This difference in energy is in units of wave numbers. It's also 63.56 wave numbers.
Wave number, okay.
Yeah, it's just weird to think of wave numbers as energy. You just got to get used to it.
How did I end up with kilograms meters squared? How did I end up with joules?
What you can do is you can put in what h bar is. And you're
No, joules times second.
yeah, and what's a joule?
Kilograms meters
Seconds.
Per second
divided by
squared. How did I get that to work out? How did I get that to work? That looks weird. I didn't worry about it. I just put kilogram meter squared because I know I is mu r squared, so I knew it had to be mass times distance squared. Maybe it was like, oh, we don't have concept previews for this, do we? How did we get the units to work out? I think that's right.
That is okay.
If we plugged in all the, I bet you that's right. Where'd it go?
Don't leave that to me with the truth. That's the same.
H bars, joules, seconds, kilograms. I shouldn't skip. If I skip steps, I'm going to screw up. Right, H bar is joule seconds. C is centimeters per second. And let's put in what we'll solve for I. That has to equal 1 over centimeters. So my centimeters are gone. Right? My
So they're left with it's joules times seconds squared and joules.
my seconds, my second squared, it's going to work out. I'll have joules times seconds squared over I equals 1. And a joule is a kilogram meter squared per second squared. So the second squareds end up canceling. It works. That would have been a good concept preview question if we had one. So it did work. We do get kilograms times meter squared. That's what I thought. I thought, the only trick is to make sure speed of light is in centimeters per second, and everything works out into standard metric units.
What did you get for your R?
127 picometers. I think all these homework questions are roughly the same thing. So if you want a pure rotational spectrum, this one, 13, just before you go, make sure you're on the same page as me, because we skipped chapter 15. Just look at the molecule, and if you see that it has a permanent it's going to have a dipole moment. It has a nice angel wing rotational spectrum. So that's what you do to answer this. If it has a permanent dipole moment, bang, you're done. Okay. So come by if you have some questions.